Hello and welcome to the Maths 2 component of the online BSc program on data science. In this video, we are going to talk about affine subspaces and affine mappings. So, before we start the video, I want to say that this video is not extremely essential to the general ideas in linear algebra that we have been looking at when it relates to data science. There is only one really important concept which we should address, and which is why we have to introduce this topic. So, I am going to be a bit brief in this video, and the idea is that if you want to really learn more, you should read a little bit of the literature, or you can ask the tutors in the tutorial sessions. So, this is not really a very integral part of the course, but there is one thing that we have to understand in this video, and I will mention that when we come to it. Okay, so let us look at affine subspaces and affine mappings. So, let V be a vector space. So, an affine subspace of V is a subset L. So, it is a subset, mind you, it is not a subspace, such that there exists V in V and a vector subspace U in V such that L is little v plus u. So, what does that mean? That means you will have to look at the set little v plus little u, where little u varies over capital U. So, essentially it is taking this subspace U and then shifting it by v, meaning you add the vector v to each vector in this subspace U. So, in particular you add it to 0 also. So, because U is a subspace, so that means 0 must be in U, which means the vector v must belong to this set L. So, any set L which can be obtained in this fashion is called an affine subspace of V. So, we say an affine subspace is L n dimensional if the corresponding subspace U is n dimensional. So, if U is n dimensional, L is considered to be n dimensional. So, the subspace U corresponding to an affine subspace is unique. So, what do we mean by that? This definition for an affine subspace says that L is little v plus capital U, V is a vector, U is a affine subspace. Maybe you could write it in a different way as V prime plus U prime, and what this statement is saying is that maybe you can write it in a different way, but the u part must be the same. So, you can write it as v plus u and v prime plus u. So, that is the only way to write it, meaning there is no choice of subspace. So, the subspace that you are shifting must be the same, and of course, this statement also implies that the fact that I made it only for u and not for v tells us that the vector v can actually be chosen in a different way. In fact, it can be any vector in the set capital L, in the affine subspace capital L. So, let's maybe ask why that is the case. So, if I can write L as, so L is v plus u and v prime plus u prime. How do I identify my set u prime? So, we just observe that both v and v prime belong to L. So, v belongs to L, v prime also belongs to L by the same reasoning. So, then what we can try and do is we can try and look at how to express v prime in terms of v plus u and v in terms of v prime plus u prime, and that should sort of give the idea for why u is equal to u prime. So, for example, if you take little u, so let little u belong to capital U, then v plus u belongs to L. So, that means it belongs to v prime plus u prime. That means v plus u is equal to v prime plus some little u prime for some u prime in u prime, which implies that u is equal to v prime minus v plus u prime. Okay. So, now the claim is that v prime minus v is in u and u prime both, and u prime is of course is in u prime. So, that means this little u will be in u prime. So, for every vector in u it will be in u prime, conversely it will be in every vector in u prime will be in u. Okay. So, why is v prime minus v in u or u prime? So, let us look at v prime minus v, and let us look at how to write it in terms of v plus u. So, well, we know v prime, well, what I meant to say is we know v prime is in L, that means v prime is equal to v plus some let us say u1, where u1 is in u. That means v prime minus v, excuse me, is equal to u1 which belongs to u, right. And you can take the negative, so that will tell you also that v minus v prime belongs to u. And the same argument done for with v and v prime, the roles changed, we will say that v minus v prime belongs to u prime. So, that implies that v prime minus v belongs to u prime. So, that means both of these vectors belong to u prime, but u prime is a vector space, right, it is a vector subspace. So, that tells us u is in u prime, and that completes the argument that I was giving here. So, the main point here is if you write it as v plus u and v prime plus u prime, then the u and u prime must be the same. So, that is what this statement here is saying, and v is not unique. In fact, as we saw, it can be any vector, because you can add some vector of u to v and express that as your v. So, the point here is that affine subspaces are translates of a vector subspace of v. Okay. So, affine subspaces are translates of a vector subspace of v. So, the main thing here is that if you have L is equal to v plus u and v prime plus u prime, then v minus u prime belongs to u and u prime, and using this you can claim that u is equal to u prime. That is the thing here, and for the other one you can just take any vector in u and add it to v, and that will play the role of v prime. So, v is not unique. Okay. So, affine subspaces are thus translates of a vector subspace of v. So, you take this u and then you translate it by v. So, let us look at a few nice videos that our team has made to explain this idea clearly. This is a video in R2. So, let us first draw the axis. So, once you have the axis, let us draw this vector u. This should have been labeled v and not u. This is little v and not little u, and this is your subspace u, which is a line, and then you translate it, and that gives you your space L. So, that is your new space L. So, this is an affine space. So, this is an affine subspace of R2. Okay, let us maybe view another video in R3. So, this time again let us draw the axis, and that is your origin, and then you draw a point, you connect that. So, that is your vector. So, this vector is being called v, and then you have a subspace, this time it is the xy axis, and then you shift it parallelly, so that it contains this vector v. Yeah, so, it is a translate of the xy axis, so that it contains the vector v, that is this point v. Okay, that is what this video is showing. Okay, so, I hope you have understood the concept of a affine subspace. So, affine subspaces are really not particularly hard, they are just translates of subspaces that we have studied all along. So, you take a subspace and you move it. Okay. So, let us put down what are the possible affine subspaces in R2. So, in R2 you can look at points, because you take the origin. Remember, the origin or 0 0 is a subspace of R2, and then you can shift this by any vector v. So, you take R2 the origin in R2 0 0 and you shift it by v. So, you do v plus 0 0 and that gives you a point, namely the point corresponding to v, and v can be anything. So, it covers all possible points in R2. So, every point in R2 is an affine subspace of R2. Similarly, we just saw the video about the first video about R2, where you had a line passing through the origin. So, that is a subspace, and then you translated it, and that gives you a line maybe not passing through the origin. So, that is an affine subspace, and then the entire plane R2, right. So, of course, there is nothing that rules out the entire plane from being an affine subspace, because in particular every vector subspace is an affine subspace, right. You could take that vector little v to be 0. So, you would get L to be 0 plus capital U, which is just capital U. So, it could be in particular an actual vector subspace. So, R2 is a vector subspace of R2. So, indeed it is an affine subspace as well. So, let us also write down an example of something which is not an affine subspace. So, affine subspaces, as we saw, they are shifts of vector subspaces, linear subspaces, right. And linear subspaces or vector subspaces, so those are always either the origin 0 0 or lines passing through the origin, or the entire R2. So, if you have a curve which is not a line, so for example, if you take the parabola y is x squared plus 1, or you take a curve like y squared is x cube. If you have not seen these curves, I would recommend that you try to draw how these look like, but they look curved like this or like this, right, and they are not. So, of course, they cannot be translates of lines or planes or points. So, these are not affine subspaces. Okay. So, let me write down here. So, if you have a point, so if I take x y, if I take this point, then how is it a subspace? So, this is my L. So, this is L, then this is the vector x y plus the vector subspace 0 0. And if you have a line, then in this case, well, how do I write lines? Well, there is many ways of representing lines. One is maybe you have y is mx plus c, right, and this line is a translate of y is equal to mx, right. So, how do I convert this into the form that I want? So, here you have to notice that the point 0 comma c is in L, and that is exactly the point that you are shifting by. So, you write this L as 0 comma c plus the subspace U, where U is given by all points of the form x comma mx, where x belongs to R. So, this is a line, this is a line passing through the origin. So, this is your subspace, vector subspace U. So, you have written L as 0 comma c plus this vector vector subspace. So, here this is your vector little v, and the entire plane, as I said, you can just write this as R2 is 0 0 plus R2, right. This is your U, this is your little v, and this is your L. Okay, so, we have expressed each of these in the form that we need to in order for the definition to work. Okay, let us ask the same question for R3. What are the affine subspaces of in R3? So, I think by now you probably have a guess about what the answer is. You have points, you have lines, you have planes. Yeah, this is something new. We did not have this in R2 because there is only one plane, the entire space in R2, and then we have the entire space R3. So, Let's also write down how any two-dimensional affine subspace in R3 can be expressed. So, two-dimensional affine subspace means a plane, right, because it's two-dimensional means you are translating a plane, right. So, then it can be written as L is V plus lambda 1 V 1 plus lambda 2 V 2, where the lambdas are in R and V 1 and V 2 are vectors in R 3. So, V is the vector that was used in the definition of L is equal to V plus U, and what is U? U is exactly this part. So, this part is U. So, U is equal to lambda 1 V 1 plus lambda 2 V 2. So, in other words, it is the span of V 1 and V 2. Yeah, this is a span of V 1 comma V 2. That's what is U. So, I mean, if we use the same idea, then points can be written as V plus lambda times 0 0, and then lines can be expressed as V plus lambda times some vector on that line. So, V 1, and planes, as we have seen, is V plus lambda 1 V 1 plus lambda 2 V 2, and the entire space R 3 is just lambda 1 V 1 plus lambda 2 V 2 plus lambda 3 V 3. Yeah, if we want to do the same idea for the case of R 2, we would have V plus lambda times 0 0 and then V plus lambda times V 1, and then the third one would be just lambda 1 V 1 plus lambda 2 V 2, because that is the entire space. It is only two dimensional. So, I hope this gives you an idea of how to of what are affine subspaces, and also the equations, the kind of equations which govern them. Okay, so, now this is the most important point about why we want to study affine subspaces at all. That is because we this particular example of the solution set to a system of linear equations is an affine subspace. Okay. So, let Ax equals b be a linear system of equations, and I want to pointedly add that I mean this need not be homogeneous, and that is really the point. If b is 0, then this is a homogeneous system, and we have seen before that the solution set is a subspace of R n. Suppose this matrix is M by n. So, this is a subspace of R n. So, we call that subspace the null space of A, right. The null space of A is exactly the solution set to this system of linear equations Ax equals 0. So, this is in the case where b is 0. If b is not in the column space of A, so in this case Ax equals b does not have a solution, right, because if b is not in the column space, that means no linear combination of the columns can equal b. If there was a linear combination which equaled b, then it would be in the column space. Yeah, so no linear combination can equal b, and that precisely means that there is no solution. So, this solution set is the empty set. Okay, so, these two cases we have seen before, and we know exactly how these two cases behave, and what we want to do in this video specifically is address the third case. Suppose b lies in the column space of A. If b is 0, then we are back in case 1. So, nothing to do. So, if b is not 0, then how do I deal with it? Then it need not be a vector subspace. In fact, it will not be a vector subspace, but it will be an affine subspace. In this case, the solution set L is an affine subspace of R n, and how do we describe it? It can be described as L is V plus n of A. What is this n of A? N of A is exactly this n of A that was here, the null space. Okay. So, you have to translate the null space by a particular solution. So, you can take any particular solution, and using that you translate the null space, and the space that you obtain, the affine subspace, is exactly the set of solutions. Okay. So, the main mantra you have to take back here is the solution set of a non-inhomogeneous or a non-homogeneous system is an affine subspace. Okay. And specifically the way to write it down is get a particular solution, translate the null space, and whatever you get is the entire set of solutions for the inhomogeneous system. Okay. Now let us come to the final thing that we want to deal with in this video. This is a slightly complicated notion, but we are just doing this for the sake of completeness. And one small idea, let L and L prime be affine subspaces of V and W respectively. So, we have seen how to define the notion of a linear transformation, right. So, now suppose, so linear transformations work between vector spaces or vector subspaces. So, now suppose we have affine subspaces, we would still like to know how to deal with functions on those, which in some sense preserve the structures that we are interested in. So, how do we do that? So, that is the idea of an affine mapping. So, let L and L prime be affine subspaces of V and W respectively. Let f L to L prime be a function. Consider any vector V in L and the unique subspace U contained in V such that L is V plus U. So, we know that L is equal to V plus U. So, note that f of V in L prime lies in L prime, and hence L prime is f of V plus U prime, where U prime is the unique subspace of W corresponding to L prime. Okay, then f is an affine mapping from L to L prime if the function g that you obtain from U to U prime defined by g of u is equal to f of u plus v minus f of v is a linear transformation. So, for a linear transformation T u to u prime and fixed vectors v in L and v prime in L prime, an affine mapping can be obtained by defining f of v plus u is equal to v prime plus T of u. So, here basically what you are saying is put f of v equals v prime, and then for any other vector or any other point on this affine subspace u, you look at v plus u, there is some u such that you have that point or vector to be v plus u, then you look at v plus u and define f of v plus u to be v prime plus T of u, then this is kind of saying that it is linear, and in fact every affine mapping is obtained in this way. So, we have g of u is f of u plus v minus f of v. So, g of u is f of u plus v minus f of v. What does it mean for this g to be a linear transformation? So, I want that. So, let us also look at some other thing, g of u prime is f of u prime plus v minus f of v. So, I want that g of I am trying to explain what this statement means. Okay. So, I want that g of u plus u prime is equal to I want this. Okay, is this equal to g of u plus g of u prime, right? This is what I want, one of the things that I need for it to be a linear transformation. Okay. Let us unravel this definition. First of all, what is g of u plus u prime? By definition, this is f of u plus u prime plus v minus f of v. Okay. So, let us put all these in here. This means that f of u plus u prime plus v is minus f of u v is equal to f of u plus v minus f of v plus f of u prime plus v minus f of v. I can cancel both sides minus f of v. So, if I do that, what I get is f of u plus u prime plus v is equal to f of u plus v plus f of u prime plus v minus f of v. Okay, and then I can take that f of v on the other side. So, I get f of u plus u prime plus v plus f of v is equal to f of u plus v plus f of u prime plus v. Okay. So, you can see here what is going on. You are taking u plus u prime plus v, and then you look at it as u plus v, u prime plus v, there is an extra v over there. So, that extra v you get in here. Okay. So, suppose you take t of x comma y comma z to be, maybe I should not have used t, let us call it f maybe. since I am using t in the previous slide for linear transformation. So, let t of x y z be 2x plus 3y plus 2, 4x minus 5y plus 3. This is not a linear transformation. Why is that? Because if you look at t of 0 0 0, then it becomes 2 comma 3, right, and we know if it is a linear transformation it would have been 0 comma 0. So, this is not a linear transformation, but this is an affine transformation. And how do I know it is an affine transformation? The reason I know it is an affine transformation is because I can write this as t of x y z is equal to 2 comma 3 plus 2x plus 3y comma 4x minus 5y, and this is indeed a linear transformation. This is a linear transformation, and this is your vector v prime. Okay, this is what the second line in that slide, the previous slide said. Okay, so this is why I know it's a linear transformation. Okay, so this is a general phenomenon, namely, if you have a linear transformation, you can, and some fixed vector w and w, then the mapping t prime of v is w plus t of v is an affine mapping from v to w. This is exactly what I did here. Let us just see what I did here. What I did is I took this t of x y z, which unfortunately this I could have called this t prime or f. So, t prime of x y z is can be written as 2 comma 3 plus 2x plus 3y comma 4x minus 5y. As I explained, you take this to be t of x y z. So, this is indeed a linear transformation. So, this is a linear transformation, and this is your vector w in here. So, this is exactly what you are doing below, and this is an affine mapping as a result. So, essentially what we are saying is this looks very much like a linear transformation, but you can shift it by a vector, and here for example you shifted it by 2 comma 3. So, usually you will have to find out what that vector is, and that vector can often be found or always be found by looking at t of the 0 vector. Yeah, if it's in this form where you have it from v to w, then you can just look at what is t of 0 the 0 vector, and that will tell you what to shift by, what to translate by. Okay, that is the idea. Okay, so let us recall what we have done in this video. In this video we have studied the notion of an affine subspace, which is nothing but taking a usual vector subspace and translating it by some vector v. The most important example that we saw is the case of the solution set of a homogeneous or inhomogeneous system of linear equations which have a solution. Okay, if x you are looking at x equals b and this does not have a solution at all, then of course it's the solution set is the empty set. So, there is no mathematics to do over there. But if it has a solution, then we know exactly what the solution set of solutions looks like. You take a particular solution and then you take the null space and translate it by that. Okay, that's how we look at, that's an example of an affine subspace. And then we looked at affine mappings, which are very similar to what we do for linear transformations, but you allow a translation again. Okay, that's essentially what we have done in this video. Thank you.